hello from me as well. And bear with me, it's the last session before the conference dinner. I am standing here alone today in front of you, but actually the science that or the projects that I'm going to present, they involve many other people, and some of the key personnel are listed here. And it combines together about 40 years of investigation of stellar outflows, and NOT has played an irreplaceable part in it. So whether it's a low mass star or a high mass star, it always starts and ends with a nebula. In the end of the star's lives, they have different explosion mechanisms where they eject their outer layers, and the remnants that are left behind emerge in the end back to the interstellar medium and into the star-forming nebula to become again part of the process. This is a simplified version, because most of the stars are binaries. That messes up their lives as well as it messes up the remnants that they leave behind. So this is what we see. Stars are spherical most of their lives, but when they explode and eject their outer layers when they die, we usually never see, or very rarely we see, only spherical remnants. We see heavily bipolar structures, filamentary natures, concentric rings, diffuse nebula, and only some of them are spherical. And we don't know exactly yet what shapes them. There are very plausible scenarios that the bipolar shapes are related to binarity. And also Carlis here before in the poster talks was saying how it's difficult also to explain Brandt nebula shaping. And here is the same, but we involve all the evolved stars. And Carlis was saying how he is investigating the central stars before they enter to these very late stages of the stellar evolution to find out what is shaping the nebula. But we investigate the nebulae themselves and how they involve in the plane of the sky. So we are, in a way, we are doing astronomy in real time, because during the human lifetime, if you choose your targets carefully, they are close to us enough, they are bright enough, then you can see their evolution in the plane of the sky. In a couple of years, in some cases even in a couple of months, you can see actually matter moving outwards, expanding into the universe. And this is the uniqueness of this project, because it is relatively easy to get radial velocities from Doppler shifts from the spectra, but to obtain also proper motions, which combines together that we can see the evolution of this nebula in three-dimensional space, is a rare thing. And this is what we are trying to achieve with our monitoring of the targets, which has been on almost 40 years. And the biggest or the most valuable that we consider in our target list is our study of symbiotic nebulae. And symbiotic stars are interacting white binary systems. They consist of a white dwarf, which has an accretion disk, and it accretes matter from its red giant companion. So the nebulosities are very rich around these targets because there are stellar winds from the red giant. The accretion disk have jets, as well as there are nova-like explosions. So usually there is a rich environment around them, which gives us the possibility to follow up their morphology during time evolution, and that gives us possibility to do the detailed dynamical and morphological study to investigate the geometry and the physics behind it. And symbiotic nebulae are particularly good targets because they often have jets, and jets are very common in astrophysics, intergalactic, extragalactic, even extra cluster, massive stars, low mass stars, but their launching mechanisms are still not fully understood, especially the collimation in evolved stars, because many evolved stars have collimated jets. And there are plausible scenarios that they are related to the magnetized accretion disks, but there is still a lot to be done in theory-wise, and theory always has to match with the observations. So we are providing the observations that the theoreticians then have to explain. And the legacy that was published in the end of 90s is our narrowband imaging survey of symbiotic stars. It was started already in the mid-80s by Hugo Schwarz. Hugo was here already mentioned yesterday, but he was also the one who started the nebulosity studies while he was still in Chile before he came to La Palma and became the astronomer in charge for the NOT. So he started in the middle of 80s observations of stellar outflows with the new technology telescope. I was still not in astronomy, but Romano was already active, and he became an enthusiastic PhD student of Hugo Schwarz. And they together started the survey of planetary nebula, but also symbiotic stars, and systematically to investigate, to look for symbiotic nebula, and also to characterize them. So, and the NOT was their main telescope that they used in the northern hemisphere. And before they started, there were only 3 extended nebula known of symbiotic nebula. One of them was discovered by Hugo, the other one they discovered together, and the third one I'm going to talk to you about in a little while. That's the most famous symbiotic nebula. And the observations at the NOT started when they had both already come on the island, and NOT was excellent, still is, and was then as well excellent telescope for that, because firstly, as we've heard a lot, they have the best spot on the mountain. It's an excellent seeing. At the same time, they offer a variety of very narrow band filters which are needed to investigate these nebulae. So altogether, already during the first observing run that they had at the NOT, during one observing night, they discovered 3 more nebulae. And altogether, they investigated systematically around 70 symbiotic stars, and they enlarged the known symbiotic nebula by 4 times. So what about me? When did I came to the picture? So right around when this paper was published, I became the university student. And 6 years later, I was also very enthusiastic. And 6 years after that, when I was in my master, I came to an international conference. It was on this island. It was in this hotel, in this very same room, and probably just standing here, being very nervous, I gave my first international presentation. I hope people don't remember it. But anyway, I got to know Romano, and I became his student to be part and to continue this project that they started already almost 40 years ago. And one of, and for 40 years, we have followed certain targets, and 30 years, almost 30 years of this has been done with the NOT, because simply NOT was not available 40 years. And 3 generations of astronomers have been part of it. It's not only me, the students, but there are many other students and other researchers who have been involved. One of the first targets that I was put to investigate is this, R Aquarii. It's a symbiotic nebula, symbiotic binary, and it is probably the most famous symbiotic star. It was discovered already 200 years ago, but no, sorry, 100 years ago, exactly almost 100 years ago, and but it still intrigues us with very interesting questions. By default, because it's symbiotic nebula, by the definition, it has a cool Mira and a white dwarf in the system. With this target, we have about 3 decades of observations with the NOT in several emission lines, because the nebulae that I will be soon talking, some of them shine brighter in certain emission lines. It has this prominent hourglass nebula. This is one lobe, and this is the other one, which we, from the expansion of it in the plane of the sky, we have calculated expansion parallax, and we can find its age, that it must have been ejected from the central star a little bit less than 700 years ago. And also from the expansion of this elliptical waist in here, we could refine the distance to it. It's only 160 parsecs away, so it's the closest known stellar jet, at least to my knowledge. But more importantly, it has a prominent S-shaped jet. We have found that the ages of the jet are oldest in the outskirts, and they get younger when we go closer to the central star, which is intuitive. The jet has been formed in several ejections, so the younger ones are closer, but it's still being formed. So some of the jet blobs are currently, as I speak, forming, probably. So we wanted to understand the jet activity. Is it continuous or clumpy, or does it alternate between the balls? And here is an animation how the jet, so this is the part which is shown here, how it changes in 10 years. And firstly, some of the parts are expanding normally. Not much happens with them. For example, the circle in here, but some parts during the time that we have been monitoring it, they shrink, they disappear, they appear again, and they get also broken up in a way. So here in the lower part, you can see that the morphology has completely changed with 10 years. Someone's laptop got wet now? So the morphology has completely changed, and this cannot be explained only with the matter moving, because we know roughly the velocities in the radial velocity domain, so it cannot be that it's only matter which has simply expanded outwards from the central star. It must be a changing, either a shock ionization or illumination changes as well. The upper part, and for this I bring this example of some of our images, these black dots that you see is the problem of this beamer. These are not real. But in the upper part, as you can see also here in the animation and here on these images, see that first of all the brightnesses of the individual blobs are changing. Some of them get brighter and the other ones get fainter. It's the time scale is about 10 to 15 years. Then they tend to get elongated. Here it's more roundish, it gets elongated, this one as well, and then eventually they break off completely. And then in the last image, this is actually not our last image, it's from 2019, we have later as well. Here it's completely, the jet has disappeared, like someone has switched off the light. So what is happening here? And these black dots, as I said, these are not, this is from the beamer, not actually the emission from the jet. So what is happening in there? We can explain it because just currently there is certain, the periastron passage, it's, as I said before, it's a binary, and the white dwarf around its orbit, around the Mira variable, is at the moment in this spot. And the northern part of the jet, some of it at least, has disappeared. And it's the white dwarf itself with its ultraviolet light which is luminizing and ionizing the jet. So it could be very well plausible. We are observers, we look from here, that when the white dwarf is here, its ionizing light is blocked by the big red giant. So this part, the jet which is behind it, may not indeed be visible. And this disappearance here between these states has happened gradually. We have some data in between as well. So it gets gradually dimmer. So now we are in the middle of this periastron passage, and the next 3-4 years, it should gradually come back, we hope. This has never been seen with the jet, that it disappears so quickly. And also, this data here, to get these orbital parameters, this has been done with the ALMA, and VLT, the sphere at the VLT is almost able to disentangle the central part, which is all very good, but still we need a telescope like NOT, where we can monitor the jet activity over a longer period of time. And also, as you can see, there are very interesting things happening in the outskirts, and this is what NOT has provided us for these targets and many other targets. And overall, the jet, it has this S shape, and it expands ballistically, but we could also see very fast moving lateral features, and they are moving up to 7-8 times faster than from the radial velocities. So again, it cannot be a real matter moving, but there has to be some other mechanism which shock ionizes or illuminates these parts on the spot there. So the evolution of the R Aquarii jet is very complex. We have to take into account that the matter, the physical matter is moving, there are changing shocks, ionization happening, illumination can be changing, and also the precession, because the jet is also precessing. And all this has to be taken into account. Our second crown jewel is Butterfly Nebula, M29, and this started way before my times. We have observations of 4 decades, and large part is again being done with the NOT. We have 3 papers which is exclusively dedicated to this target, and few others where it plays a smaller part. It has also complex nested system of lobes. It's highly bipolar, and luckily to us, it's like almost edge on, so we can see what is happening here in the central parts. It has the neutral shell, which is visible here, the fainter one, and it becomes, it unites in the outer parts with the outer lobes and these dusty blobs on both sides. From the expansion of these blobs, the plane of the sky, we could refine the distance to the target, which is 1.3 kiloparsecs, and also we could estimate the inclination angle of the whole system, which is 18. The inner lobes, which are visible on this image with 2 globes and arcs, this is ionized gas, while the neutral shell and the outer parts are more scattered light. And our biggest interest, because the biggest changes are happening here in the ionized part. So we have proposed, and we are sure that it has a corkscrew geometry, and there is the inner part of it is rotating, which is best visualized here in this animation, which combines 13 years of observations. And as you can see, it's like a lighthouse effect, which is just going around, and these knots are moving along this direction. And here there are some still images from the same animation, and you can see that these are these blobs that are moving, but the upper part is sort of staying roughly at the same place, and then seems to perform this kind of a hoop, and I'll come back to that a bit later. 3 minutes, okay. So we can see time delay between these 2 blobs, as well as with the northern blobs, with the southern blobs, and that tells us that we are dealing with the actual particles or the shocks created by the particle jet, because if it only would be a light beam, which some other authors have proposed, then you wouldn't see any time difference in the propagation of the jet. But we see it, and from the amount of time delay, we can calculate that we are dealing with a very high velocities. The particles must have very high velocity. It's unusual, up to 16,000 kilometers per second. So this is unusual for planetary nebula. The jets in symbiotic nebula have higher velocities. It's still a bit too high, but it's the best case scenario that there is. And in this scenario, if it's a high velocity particle jet, there is no other ionization needed to explain this rotating pattern in here, because usually also the ultraviolet light from the white dwarf, for example, illuminizes the nebulae. And another interesting point is that it has a mirror symmetry. So usually if you have accretion disk, then your jet is launched parallel to both sides. But this one seems to do this. So if this is the upper jet, this is the lower jet, and here is the central star. So it comes towards you, but this is exaggerated, and then it goes behind. It comes towards you, and it does this. So this is the only thing which can explain this mirrored morphology that it has. And it is plausible that the red giant, which probably part of this system, the wind has created a density, it has a varying density distribution in these lobes that it has, so it could be that it forces the jet to be bended when it goes around in its road, or how do you say, in its road, inside the inner cavities of these lobes. And the pattern rotates with a period of 90 years. Here on the image there are 13 years. So what happened afterwards? This is really hot from the oven. This part was published, but this part I was using not archive last week to retrieve some of the data. Friday, that was Thursday, Friday I was still reducing the data, and this data, the last was done just a few weeks ago. The matching is still not perfect, so it's just for a few glimpses to show you that this pattern, which here moving, has now disappeared, so that's like extra 10 years. This hook here has becoming brighter and bigger, so it sort of seems to go towards the central star, which is weird, but we explain it, we cannot really explain very well, but it's somehow the high velocity particles are just, they arrive to the end of these cones and they sort of flow around or along these cavities. So we are continue all our targets. These were just few highlights. I am also doing the similar long-term monitoring as well as starting the systematic search for extended shells around B Brackett stars. But I'm running out of time, so I will wrap up with coming back to the birth of the stars. With Amanda Tupvik from the NOT, I was also part of investigating the kinematics, proper motions again, and radial velocities of the protostellar jets. And here there is 2 decades of NOTCAM observations. Biggest outcome and surprise for us was that there are time variable, the blobs. We have investigated about 50 blobs we have identified, and 30 we get proper motion, and they have time variable velocities. And the same, some of them disappear, some of them appear. So before I showed you evolved stars, they have jets, and now before the stars are born, they also have jets. So jets are everywhere, and there are always lots of questions about them. To wrap up, what should you take home? So I think I don't have to convince you that the scientific legacy of the NOT is huge for us, for everyone who are here. But I would also like to point out, as an ex-NOT student, that the Johannes Andersen student program is probably the best business that the NOT has. They give something to the students, and also students get a lot back. And in return, even when we leave, I was here 10 years ago, we continue using the NOT. So we have very regular users for many years. And last but not least, the family that the NOT provides when they come is also very important, because they all leave homes. Moms and dads are worried, so they get new moms and dads here. And Johannes also played a big part in the NOT family, even though he was not permanently here, but whenever he came, he was more like a grandfather to us than the director. Thank you.